Welcome back to this VLSI technology lecture. So in the last lecture, we have seen how to obtain the wafer from the single silicon crystal ingot. So various steps that we have followed to obtain the wafers from the ingot are we have already discussed. So those operations like shaping, sewing operations we have seen. We have seen the mechanical lapping operations. We have seen etching process, chemical mechanical polishing process. So after doing the various steps, we can get a particular wafer. So after getting the wafers, we need to keep in mind that ultimately we have to make a certain devices onto this particular wafers. So after making this wafers, first of all, you must be aware that we have to get a particular wafers of particular specifications. So we have a certain specification mentioned over here. You can see that we can have a different type of wafers of different specifications. So we can have the different parameters like 125 mm diameter, then 150 mm diameter, 200 mm diameter, and 300 mm diameter. So these are the different diameters that actually we are nowadays we are fabricating. So different diameters, and there may be a little bit error in that diameter. It is not exactly 125 mm. It can be could be plus minus 1 mm or plus minus 1 mm everywhere you can find. So we are having a diameter of particular diameter we can get, and then we can have a different thickness. We can have different primary flat length value. We can have different secondary flat length value. We can similarly have a particular bowing parameter, total thickness variation, and surface orientation. So once we obtain a wafer of a particular specification, okay, after obtaining the wafer, we need to go for the fabrication of the device. For example, we already seen that for the IC fabrication, one of the most basic element that we are using is our MOSFET. Okay, so we can use metal oxide semiconductor devices as a basic element to make our ICs. So now we have to see how this particular MOSFETs will be fabricated onto the wafers. That we have to see in this particular lecture. So as we are aware that when we are making a wafer from the ingot, you have already seen that we are going through a lots of mechanical and chemical processes. Okay, so when we are going for the mechanical and chemical processing, we know that because of this there may be a certain type of contaminants that may be available onto the wafer surface. So as we know that whenever there are some contamination available onto the wafer surface, it may incorporate into your devices, and later on it is going to affect the device performances. So what we need to have is we need to have a very ultra pure wafer. So we need to clean the wafers repeatedly so that this wafer should not be contaminated by any kind of contamination, whether it is coming from the mechanical operations, or it may be coming from the chemical operation, it may be coming from the environment. Okay, so whatever may be the reason, whatever may be the source, this contaminant should be removed. So basically we need to understand how this contaminants, what are the sources of the contaminants, and how these contaminants will be removed. Fine. But before discussing that particular contaminants and how it will be removed, we need to first understand, if we are going to make a particular device like MOSFET, then what are the different steps that our wafers will go through so that we will be able to make a particular transistor. So I will be discussing in this lecture today about how this NMOS can be fabricated. Okay, so we will be discussing this. So let's begin this particular discussion. So while making fabrication of the NMOS transistor, we can have these two different processes. Either we can follow the metal gate process, or we can again follow the polysilicon gate process. These two processes are actually most prominent. Nowadays we are using polysilicon gate process, but I will be discussing in this particular lecture the metal gate process. Fine. So while fabricating of the NMOS, we can categorize the all fabrication steps, all basic fabrication steps into 5 categories. Okay, so basically the first step you can see, first of all, while fabricating a particular NMOS transistor, we need to have a wafer. Okay, without wafer we cannot make anything. Fine. So how to get this wafers? We already know that To get the silicon wafers or germanium wafers or gallium arsenide wafers, first of all, we need to make a particular single silicon crystal ingot, and out of the ingot, we need to cut the wafers by following the different processes. So how to get this single silicon crystals? Okay, by following the Zogralski technique. If we want to get the gallium arsenide single silicon crystal, then we have to follow the Bridgman technique. Fine. These are the different techniques by which we can make the single silicon crystal, and out of this we can make our wafers. Fine. So this is obviously we need to have the wafers. Without wafer we cannot fabricate anything. Okay. So onto the wafers we have to make our device. So this is one of the things that we need to understand. Next, the next process is our oxide formation. Okay. I will be telling you step by step while discussing about the NMOS fabrication, but what are the major categories that you need to understand here? So we need to do the oxide formation. Okay, so while oxide formation, oxide can be formed either following the dry oxidation technique or it can be a wet oxidation technique. Fine. Similarly, we have to go through a process which is called as the patterning. What is this patterning? I will be explaining in the detail. Okay. So while patterning, we have to talk about these terminologies. Okay. Photolithography process, etching process, photoresist, and photomask. Okay. Then we need to dope a certain regions. Like if we are fabricating NMOS transistor, obviously we need to have the regions which are N doped. Okay. N plus doped. So we need to go for the doping process. Okay. So this doping process maybe either we can use diffusion technique or it may be your ion implantation technique. Similarly, multiple times we need to deposit different layers onto the wafer surface. Okay. That layer could be our dielectric layers. It could be our organic layer, it could be our metallic layer. Okay, so that layers can be deposited based on the type of layer that we want to deposit. We can follow these methods like CVD, MOCVD technique. Okay, it's called as chemical vapor deposition or metal organic chemical vapor deposition. Then PVD is sputtering technique, vacuum deposition technique. These are the different techniques. Okay, later lectures I will be discussing all these techniques in the details like diffusion technique, ion implantation. All these techniques I will be going to be discuss in detail in the later lectures. But right now you have to remember these are the basic four categories I can say. Wafer is obviously we need to have, and after that these four processes we need to go through. Okay, so while writing these four processes, you do not confuse that we every time we have to follow this sequence. Okay, and there may be sequences that it's not like we have to just one time use the patterning or we are going to use the deposition just one time. It may be used multiple times. Okay, that you will be able to understand when I will be discussing the metal gate process. Okay, for NMOS fabrication. So these steps can be followed it's not necessary that sequentially. Okay, it can have any order. Okay, it can have any order and it can be used multiple times. Fine. So now we have to look at how this NMOS fabricated using the metal gate process. Fine. So, so what is the very first step while making an NMOS using the metal gate process is, first of all, we have to take a P-type substrate. Okay. So first we have to take the P-type substrate. As I already explained you that while growing the single silicon crystal, we can add a certain dopant material into the melt. Okay, this we have already discussed. So what we can do is we can add a particular dopant into the melt and then we can grow the crystal. So after growing the crystal, when we cut the wafers, that crystal will be already a P-type substrate. Fine. So that way we can get our P-type substrate, or otherwise we can also have some other method to get the P-type substrate. So first we have to take the P-type substrate, or you can say that it is a P-type wafers. Okay. After taking the P-type wafers, what we have to do is we have to place this particular wafers onto a very high temperature furnace. Okay. So for oxidation process, right? So what we have to do is we have to first place this particular wafers onto a particular high temperature furnace, and then we have to heat it up to 900 to 1200 degrees centigrade. And then the top of this particular surface will get oxidized. Okay, we have to pass the oxygen and then it will oxidize. So once it will oxidize, it will make a SiO2 layer. Okay, the top layer will become silicon dioxide. So it will be get oxidized and one layer will be growing. So what we have to do, we have to first take the P-type substrate, then we have to grow the SiO2 layer using the oxidation process by following a thermal, you can say it is, we are having a thermal we are having a high temperature furnace. Okay, so this way we can grow our SiO2 layer. As I have already explained that SiO2 layer, actually it will be acting as a mask for the dopants. Okay, that we can see in the next slide. Fine. So after growing this SiO2 layer, what we have to do is, after growing the SiO2 layer, onto the SiO2 layer, we have to again deposit another layer, which is our positive photoresist. Okay, what we have to do is we have to coat a positive photoresist layer. Okay, it will be an organic layer. Fine. So we have to particular photoresist we have to coat over the particular over this particular SiO2 layer. Fine. So what is the use of this particular photoresist that we need to understand? So obviously, as it name suggests, okay, it's photoresist, means it is going to resist the light. Okay, whenever we shine a particular light of particular wavelength, then it is going to resist this light. It will not allow the light to pass through this particular layer because it is resisting the light. Fine. So when we are saying it is a positive photoresist, what does it mean? That when the photoresist could be positive photoresist, it could be also a negative photoresist. Okay, so in this case, when we are having a positive photoresist, it means that whenever we are shining a light of a particular wavelength, so those area which are actually exposed to the light, okay, those area is going to be polymerized. Okay, what we are saying is, if a particular section of this particular photoresist layer is exposed to our light, normally we are using the UV rays, okay, ultraviolet rays we are using. So when we are shining this particular layer from the top, and UV rays are coming from the top, okay, and if a certain section of this particular photoresist is get exposed to this UV rays, so those sections which are exposed to the UV rays, it will get polymerized. Okay, so once it is getting polymerized, we can have a particular photoresist developer solution. Okay, it is again a chemical. Fine. So in that particular developer solution, if we dip this entire wafer into that, then that area which was exposed to the UV rays will be actually dissolved into that particular developer, and it can be removed. Fine. So that is the thing. Means it is, if it is a positive photoresist. If it is a negative photoresist, obviously that particular area which is exposed to the light will become hardened. Okay, it will not become softened. Okay, it will become hardened, and it cannot be dissolved into the developer solution. So it cannot be removed that time. So what is the positive photoresist? It will get softened, or you can say it is getting polymerized, and it can be easily removed by applying a particular developer solution. So after coating this particular photoresist layer, this is our step number 3 now. So what we have to do is we have to go for the step number 4. We have to use the lithography using photomask. So what we have to do is, first of all, we need to place a particular photo mask onto the top of your wafer. Okay, so this way we have to place a particular photo mask. Okay, so what is this photo mask? Okay, try to understand. In this particular photo mask, we are actually having a certain openings. Okay, these are our windows. Okay, this area is actually, it is a cross sectional view. We are seeing this wafers from the front side. Okay, so if we see from the top side, you will find that it may have some square shape. Okay, here it is, when we are seeing it, we are seeing it from the cross sectional view. So when you see it from the top, okay, this entire photo mask will also having a rectangular shape. Okay, a particular rectangular shape, and in between there will be a small window. Okay, these are the small windows. Okay, these are the small windows. So you will find that there are small windows. Okay, so what is the use of this photo mask? The use of this photo mask is, when we shine the UV rays, fine, these areas will not let the light go, means the light cannot penetrate through this particular area. Okay, these are the photo masks, so it will be masking the light. Fine, but the light can only pass through these windows. You can say it is openings. Okay, these are the windows, means these are the openings. Okay, so through this the light can pass, through this the light can pass, and from all other places the light will be masked. It cannot go to the this particular photoresist layer. So now after having this particular photo mask, we have to shine the light once the UV rays is shined over here, then it will be penetrated or it will be passing through the window, and then this light will come out, and then it will be going to shine this, or going to shine this particular photoresist layer. Okay, it is going to shine this particular photoresist layer. So this area only going to exposed with the UV rays. Okay, so what we can say, we are doing the selective exposure of our photoresist. What we are doing here is we are doing the exposure of our photoresist, but it is doing selectively. We are not doing it means the entire photoresist is not going to be exposed to the UV rays. Only a certain portion of the this particular photoresist layer is going to be exposed with this UV rays. Fine. So what happens when we shine this particular light? As I already explained that this is a positive photoresist. So what happens because of this interaction of the light? Okay, this is our photoresist material. Okay, so because of the UV rays light, what will happen when it interact with this particular photoresist material? This particular section will become polymerized, or we can say it will become softened. Okay, it will become softened. Okay, so these area will become softened and all other area will remain hard, you can say, or it cannot be removed. Fine. So this particular section will become softened or polymerized. Fine. So what we are saying, polymerized photoresist due to exposure of the UV rays. Okay, so what I am showing is this section becomes polymerized. Okay, this section becomes polymerized. So now when this section gets polymerized, what we can do is we can easily remove this section by applying a certain developer solution. Okay, so we can apply a certain developer solution, and this way we can remove this particular section. Our next step is the step number 6 is etching of the polymerized photoresist using suitable developer solution. Fine. So what we have to do is we have to put this entire wafer into a particular developer solution, and because this is already become polymerized or softened, so this will be dissolved into the that particular solution, and then this area will be opened. Fine. So now we have opened this particular area. Fine. So once this is opened, now this window is opened over here. Now what is our task is, why we are doing is because we need to deposit a layer of N plus resin over here. Okay, so do not forget that this is our P type substrate. Okay, I have not written over here, but it is a P type substrate we have taken initially. Fine. And because we are fabricating a NMOS transistor, we need to make a N dope resin over here. Fine. So now we have opened this particular window. Now what we have to do is, because we have to go for the doping process, we have to selectively remove this particular SiO2 layer. We have to selectively remove this SiO2 layer. So how it can be removed? We have to use a particular chemical. Okay. So what we have to do is we have to do a etching process. Okay, in that it is a chemical etching process. Fine. So etching of the SiO2 layer using the HF acid. Okay, so what we have to do is we have to use the hydrofluoric acid, and that acid is going to interact with this particular SiO2 layer. Okay, and then after some time this layer will be removed. Fine. So this layer will be removed, and we can already see in that this layer, okay, the layer under the our photoresist cannot be means attacked by our HF solution. Fine. So it cannot be attacked by the HF solution. That's why it is means remains there. These layers are remains there. Okay, these are the SiO2 layers, but the window that we have made, only from that window SiO2 layer can be etched out. Fine. So this SiO2 layer has been removed by following a particular particular acid. Okay, so we have followed the we have used the hydrofluoric acid for removal of our SiO2 layer. Now after removing the SiO2 layer, okay, so why we are removing this? Because we have to go for the doping process of our N plus resin. Okay, so we have to dope this particular P type substrate with the N plus dopants. Fine. So to doping process, we need to remove this SiO2 layer, because I told you that this SiO2 layer is acting as a mask for our dopant. Okay, so if there is a SiO2 layer, then the dopants cannot be incorporated into the P type substrate. So that's why we need to open this window, okay, before starting the doping process. So as I explained in the first slide that about the doping can be done by the ion implantation technique or the diffusion technique. So either way we can go for the doping. Fine. So before the doping process, what we need to do is we have to remove these layers. Okay, once we have opened the window, now we can remove these particular layers. Okay, so to remove this particular photoresist layer, okay, what we have to do is we have to strip it away by using a Piranha solution. Okay, so Piranha solution, or it is called as the Piranha aging. Okay, so by Piranha aging, again it is a chemical. Okay, so in that chemical we have to use the H2SO4. It is actually basically a mixture of acids like H2SO4 and H2O2. Okay, it will be available in the ratio of somewhere around 3:1. Okay, in that ratio we have to take, and then we have to make a Piranha H, and then within that Piranha H we have to put this entire wafer so that this area will be removed. Okay, this particular top photoresist will be removed. So after removing this photoresist, okay, we are going to get this particular layer. Okay, this type of a structure you will be getting. So after doing this operation, now what we have to go for, we have to go for the doping. Okay, so after doing this doping, you are going to get, it can be either diffusion technique, okay, or it can be an implantation technique. So do not bother about its details. I will be discussing in the later lectures what is, how this diffusion will be done and how the implantation will be done. Okay, what are their merits and demerits, everything I will be discussing in the later lectures. Fine. So this way we have to grow our n plus region. So once we have grown the n plus region, okay, source and drain we have grown by the doping technique. After doing this, okay, what is the next step? Okay, the next step, you know that in the NMOS transistor what we need to have is we need to have a particular thin oxide layer, okay, at the gate region. Okay, then we have to do the metallic connections. Okay, metallic connection we have to make from this n plus regions. Fine, so that we have to perform. So to do that, what we have to do is again we have to cover this entire surface, okay, these openings with the SiO2 layer. So what we have to do is we have to again go for the oxidation process. I told you that this oxidation process or patterning process or diffusion generally we do once, and deposition of the different layers will be done multiple times. Okay, so again what we are doing is we are going for the oxidation process, and then again we are growing the SiO2 layer. So now after doing this, this entire surface again will be covered with the SiO2. So once it is covered with the SiO2 layer, okay, again we have to go for the patterning process. Okay, so what is patterning? Patterning means the way you have seen that we have placed a particular photo resist layer, then we have placed a particular photo mask, then the photo mask was actually containing a particular pattern, okay, particular window, and that window or that pattern is actually transferred to this particular SiO2 layer. Okay, so that is called as the patterning process. Right, so again what we have to do is again we have to go for the patterning, which is photolithography process. Okay, so in that what we have to do is again we have to put a positive photoresist. Okay, after coating the positive photoresist, then again we have to take a particular photo mask. Okay, you can see in this photo mask the pattern is different. Okay, we have taken a different window. Okay, that time we had just two windows. Okay, and just for the n plus region, one window was like this and another window was like this, but now we are having a different window, you can see. Fine, so now this pattern is to be transferred to this particular device. Okay, so how it will be done? Again we have to place a photo mask. That photo mask will have a different pattern on that. Okay, and then again we have to shine the UV rays. Once we shine the UV rays, the light will be passed through this particular windows, and the reason under these windows get polymerized, and that can be removed by having a particular chemical solutions, or you can say it is a developer solution. Okay, so that this portion will be removed, this portion will be removed, and this portion will be removed. Okay, so after doing this, you can see this will be polymerized. Okay, this will be polymerized, you can see, because it is exposed to the UV rays. This portion is getting polymerized, this portion is getting polymerized. So once this portion will get polymerized, now again it will be dipped into a particular developer solution, and these layers will be removed. So after removing these layers, again what we need to do is again we have to strip away the no, first of all we need to remove this SiO2 layer. Okay, we need to remove the SiO2 layer from this window only. Fine, so again it will be put into our HF solution. Okay, HF acid. So this particular layer under this particular open window. Okay, this SiO2 layer will be removed, this SiO2 layer will be removed, and again this SiO2 layer will be removed. So this way we have to remove the SiO2 layer. After removing this SiO2 layer, what we need to do is again we have to remove this particular photo resist. Okay, so again we have to use the piranha solution, and then again this all layers should be removed. So after removing this layer, what we have to do is, because we have to grow a thin oxide layer, okay, for the gate. Okay, we have to make a gate oxide layer. Okay, very thin oxide layer we have to grow. So after removing this, we have to again grow a very thin SiO2 layer. Okay, so a very thin SiO2 layer will be grown like this. Okay, so I am deliberately I am showing this with a different color, but it is SiO2 layer. It should be shown like the same SiO2 layer, the way I have represented in this. Okay, it should have the same pattern, but just to make it clear that I am growing a thin SiO2 layer, I have used a different structure or different pattern here. Okay, so that you please try to understand. So after growing this thin SiO2 layer, okay, once we grow the thin SiO2 layer, again what we need to do is we need to deposit the metals. Okay, because it is a metal gate process. Here we need to grow the metal. Okay, and before that what we have to do is again we have to connect a metal to this particular N plus region, another metal to this N plus region. Okay, so that the connection can be made. So what we have to do is we have to remove this SiO2 layer, this SiO2 layer, but we have to keep this SiO2 layer as it is. Fine. So again, what we have to follow is, again we have to follow the patterning process. Okay. So again we have to follow the patterning process. Then again we have to what we have to do is we have to remove this layer. So again we have to place a particular photoresist layer. We again have to use a particular photo mask. Then again we have to use the acid solution. Okay, then we have to remove these layers. Okay, these layers we have to remove, and this layer has to be intact, it should not be disturbed. Okay, so that steps again we have to follow. So after growing this thin SiO2 layer, after doing the patterning process again, we have to get this type of structure. Okay, so removing thin SiO2 layer from all over the surface except the gate region. Okay, and how it will be done? Again by following the same patterning process. Okay, again we have to follow the same patterning process. So this structure we have to get, and now we have to go for the metal deposition. Fine. So what we have to do is we have to deposit a metal. So here I am not explaining you what kind of deposition technique we are using, because there are so many ways, like chemical vapor deposition I have told you, a sputtering technique I have told, PVD technique I have told. Okay, so vacuum deposition technique we have. So many techniques are there. So what kind of metal we are using and how it can be deposited, I will be discussing in the later sections. Okay, so we have to deposit the metals for contact. So after depositing these metals, you can understand now, after depositing these metals, you can see all are short circuited, because all over the places we have the same metal and they are all interconnected. So they are all short circuited. Okay, so we cannot have this type of metallic connection, because we need drain terminal should be isolated with the source terminal, and the gate terminal should be isolated with both the drain and gate. Okay, so it should have three terminals. Fine. So again what we have to follow is, again we have to follow the patterning process. Okay, and we have to selectively remove the metal portions. Okay, we have to make it isolated by doing the patterning process. After doing the patterning process, we can remove the metals, okay, from all other places where it is not needed, and then we can have a separate terminals for our source region, drain region, and the gate regions. Fine. So what we have to do, we have to selectively remove this by following the patterning process. Again, remove, just remember this. Okay, so selectively we have to remove the aluminums, and now this will become isolated. Okay, this will become isolated. And the finally what we have to do is, finally we have to do the overglassing process. Okay, and in the overglassing or passivation, we have to completely cover the device with the SiO2 layer, and the metal connections or the metal contacts will be available at the outside. Okay, and there we can make the lead connections. Okay, and this will become our like source terminal, drain terminal, and gate terminal. So I hope you must be aware of must be able to understand how we are making the NMOS transistor. Okay, NMOS fabrication. What are the different? What are the basic steps that we need to follow? And you can must be able to understand that there are certain processes like oxidation, there are certain doping process, there are certain patterning process in which we have to follow the photolithography, in which we have to place a positive photoresist, then we have to follow the photomask, then the photomask pattern will be transferred to these devices. Okay, and this then the deposition of the different layers like metallic deposition or the SiO2 layer deposition. Okay, so many things are there. Okay, so many things are there, so that you have to remember that this particular devices, whatever MOSFET, like I have shown you here, just like for a single transistor, single MOSFET. But basically when we are fabricating an IC, we don't fabricate a single transistor. Okay, there will be a huge number of transistors, huge number of such patterns will be available on the photomask. Okay, huge number of patterns. Okay, and accordingly we have to grow a million number of transistor or billion number of transistor onto the same way, so that way we can do it. So as you know that it is when we are discussing this NMOS fabrication, from this discussion only you can understand our wafer is actually going through a lots of chemical processing. Okay, lots of chemical processing, lots of like deposition technique, then it is going through some organic compound like our photoresist. Okay, so it is going through so many chemicals, so there is a chances and there is 100% chance that our wafers is going to be contaminated. It is going to be contaminated. And here I have not shown you. Okay, but multiple times while fabricating a device, okay, fabricating any device, multiple times we need to keep on cleaning the wafers. Okay, keep on cleaning each and after each and every steps, we need to keep on cleaning the wafers. Okay, so that any because these chemicals are not actually needed into our devices. It is the chemicals that are actually involved in only the processing steps while fabrication. Okay, so it should not have any contaminated portion that may be available within the device. If any contamination due to chemical like HF solution, or it may be a piranha etching, or it may be some organic compound, if it is available onto the device, it is going to means badly affect our device performances. Okay, so that we need to understand, and then we have to think of how we have to remove these contaminants while fabricating the devices. Fine. So in our next lecture, we are going to discuss about how these contaminants will be removed and what are the different sources from where we can have the contaminant onto our wafers. Fine. So thank you for watching.